Let's take a look at rational expressions and their graph. Now remember, rational expressions are functions or things that kind of look like this, kind of like 2x plus 3 over, I don't know, x squared plus 5x minus 2. Right, generally it's a fraction where we have variables in the denominator is what we're talking about when we're looking at rational expressions. Well, there's a few things that we want to cover before we can do this. Now, there's a lot of different features to a graph for a rational expression. First off, let's take a look at something called end behavior, which we've already looked at for polynomials, but not for rational expressions. Now, we're looking at a new notation that we haven't seen before. Let's say I gave you this is our graph. Let's say y is equal to x, 1 over x plus 3. And I said, what's happening at the end? So remember, the end behavior is what's happening as we get farther and farther away from the middle or from the origin. So what if I said, what happens as, now here's our new notation, as x approaches, let's say, infinity. The way you read this little arrow here is approaches. So basically what we're going to do is we look at this expression, we let x get bigger and bigger and bigger. What happens to this expression here? Well, think about it. You have the number 1, and if the bottom's getting bigger and bigger and bigger, you're cutting this up into smaller and smaller pieces. So as x goes to infinity, y approaches 0. Right? So think about it. As we get down to the graph and we go this way, let me do a quick little here. I don't know what the graph's doing in the middle, but I know as x gets bigger and bigger and bigger, y is going to head towards 0. Now we got another little notation here. Since x is positive, right, we're heading out toward positive infinity, that would make this entire expression positive. So we're heading towards 0, but all the y values are positive. So to the upper right of that, I'm going to put a little plus, which means I'm heading to 0, but I'm heading towards 0 from the positive side. So here's the line y equals 0. As I head this way, my graph's going to head towards this, but from the positive side. So you can kind of think about it, whatever the graph's doing, it's going to head down towards there. Now it never actually gets to 0 here because it's just getting smaller and smaller and smaller. So that just gets closer and closer to it. So if we ask the same question, what if we go towards negative infinity? Well, if x is going to negative infinity, that means the x's are negative values. So if we put negative values in here, of course a very big negative value plus 3 is still negative, this is also going to head towards 0 again, right? Because the bottom's still getting bigger and bigger and bigger, just negative. But this time we're going to head towards 0 from the negative side. So as I head this way, I'm again heading towards this line y equals 0, but from the other side, so the graph is kind of heading up like that. So notice that this is showing us what the end behavior is doing. Now since y is approaching 0 from the left and the right, this line right here is called an asymptote, and it's actually called I'll put a dotted line right there. This is a horizontal asymptote. An asymptote is generally a line that you approach. For most asymptotes, you can't touch them. For horizontal asymptotes, sometimes you can actually touch them, but generally you rarely do it. Okay, so the end behavior of a graph is as y gets bigger and bigger and bigger, it gives you these horizontal asymptotes. The good news for us in a class like this is we actually just have a set of rules. So our rules for horizontal asymptotes are this. Now this is going to start out scary looking, but here's the idea. If we have a rational expression, and remember a rational expression is just a fraction of polynomials, which means we have some generic polynomial on the top, a sub n, x to the n, plus all the way down to, you know, remember these kind of generic looking ones. Some other one on the bottom, that's an m. Okay, here's the idea. the degree of the top polynomial is n, the degree of the bottom polynomial is m. So here are the three cases you have to memorize. If n is less than m, the horizontal asymptote is the x-axis, which of course is just y equals 0. If n is bigger than m, you do not have a horizontal asymptote. And if n is equal to m, the horizontal asymptote is the line y equals just the ratio of the lead coefficients. However, there is one more case where you're like, it can't be. They're exactly that's all the cases. Either it's less than, greater than, or equal. Well, if n is bigger than m by 1, then there is a slant asymptote. We'll get to a slant asymptote in a second to show how to find that. Okay, so the idea for end behavior is what happens to the graph as x gets bigger and bigger and bigger, either in the positive or the negative direction. Now, you can summarize all this into 3 rules that we did here. You do need to memorize those. Let's take a look at a couple more different types of asymptotes. And those will be our horizontal asymptotes. Let's take a look at vertical asymptotes. Okay, vertical asymptotes occur where the denominator equals 0, but the numerator does not. All right, here's the idea. Again, we have rational expressions that, I don't know, something like we had here. Notice here, in this denominator, that would be equal to 0 at x equals -3. Now, since x can never be -3, there has to be a place in the graph that we can never exist at, and that would be the line x equals 3. So for vertical asymptotes, there's a physical barrier in the graph that you can't cross. So if we were to just think about this graph right here, over here at x equals -3, there would be a line that the graph can never touch, right? Because x can never equal -3 because we're not allowed to divide by 0. Now the question then becomes, what happens to the graph at this point? Because you know, it's got to exist everywhere else. But what happens as we approach this value? So let's take a look at this easier expression. What if I gave you 1 over x? Now you can definitely see for this one, x equals 0 would be a vertical asymptote. But what happens to y? What happens to y as x gets closer to 0? Now let me change my picture here just a little bit, just so we can get an idea of what's going on for this graph. Now x equals 0, of course, here is the y-axis, so I'm going to put my vertical asymptote over here now. Now again, here we can approach 0. When we're approaching infinities, you can either go towards infinity that way or go towards infinity that way. However, when I'm approaching 0, I can actually approach it from 2 different directions. So as x approaches 0, let's say with a plus there, and that means values bigger than 0. So here we're on our x-axis, and I'm approaching 0 from values bigger than 0. What's going to happen to this expression? Well, if the bottom's getting smaller, that means the entire thing's getting bigger. So as x gets smaller and smaller and smaller, y is getting bigger and bigger and bigger. That means y is going to approach infinity. Now, is it going to approach positive infinity or negative infinity? Well, since we're approaching 0 from above, that means all the x values are positive. So a positive divided by a positive would be we approach positive infinity. As we approach x, as x approaches 0 from values less than 0, so now think about it, we're heading this way, here all our x values are negative. A positive divided by a negative is going to give me a negative number. And since we're taking a number and dividing by something that's getting smaller and smaller and smaller, it's getting bigger and bigger and bigger. Okay, so here's the idea. As I'm heading towards this vertical asymptote, I can't cross it, right? Because I'm never allowed to be zero. So you kind of get an idea anyway what's going to happen. Graph has either got to turn and go up, or graph has got to turn and go down. Well, as we approach zero from the positive side, it's got to turn and go up, which means as I head this way, I don't know what's going on over there yet, as I head this way, it's got to go up. On this side, as I approach zero from over here, it's got to go to negative infinity, which means it's going to turn and go down, kind of like that. Again, I haven't really talked about what the end behavior of this graph is, but as you see, as you approach a vertical asymptote, the graph is either going to head up towards an infinity or down towards negative infinity. And we'll see how that works out when we go to actually graph a couple of these. All right, the one other type of asymptote that we kind of talked about that we can have is a slant asymptote. And again, this occurs when the degree of the numerator is greater than the degree of the denominator by 1. So it'd be like the top is x cubed, the bottom's x squared, right? So something like this. Let's say we had like y equals 4x cubed plus 5x minus 3 all over 5x squared plus 3x plus 2. Right, the degree of the top is 3, the degree of the bottom is 1. So according to our horizontal asymptote rules, there's no horizontal asymptote. But since the degree of the top is greater than the degree of the bottom by 1, then this would have a slant asymptote. Now all that means is our horizontal asymptote, which is normally of course horizontal, is going to be tilted up at some angle. Now to find it, do long division. The equation of the slant asymptote will be y equals the answer without the remainder. All right, you'll see what I mean by this in just a second. So let's say if I gave you y equals x squared plus 3x minus 4 all over x plus 2. Now if we were told to find asymptotes here, we'd have a vertical asymptote anywhere the denominator was equal to 0. Well, of course that's going to be equal to 0 when x is negative 2. Looking at horizontal asymptotes, according to our rule, the degree of the top is bigger than the degree of the bottom, so we do not have a horizontal asymptote, but since the degree of the top is bigger by 1, we do have a slant asymptote. So what we want to do, let's say I'll move it over here, we're going to do x plus 2 into x squared plus 3x minus 4. All right, what do we have to multiply x by to be x squared? That's x. Distribute, that's x squared plus 2x. Subtract, that gives me x. What do I have to multiply x by to be x? That's 1. Distribute, subtract, that gives me negative 6. So there's my remainder, negative 6 over x plus 2. Okay, so the slant asymptote will be the line y equals x plus 1, right? It's this piece right here without the remainder. All right, so there's 3 types of asymptotes that we're generally going to look for. We're always going to look for horizontal and vertical asymptotes to help us draw the graph. And in the one weird case where we don't have a horizontal asymptote, we may actually have a slant asymptote, so we need to be able to find that.